Welcome back to Algorithms and Uncertainty. In the last lecture, we've already introduced the framework of online competitive analysis, and we've already seen one problem and two algorithms for this problem, namely for ski rental. Today we'll consider a different problem, and again we'll introduce an algorithm for this, and we'll also show that this algorithm is approximately optimal in the online setting. And this problem will be online Steiner tree. The Steiner tree problem is a famous combinatorial optimization problem, and we will see it in different versions with uncertainty throughout the semester. So besides learning about the online Steiner tree problem, today we'll also see fundamental techniques how we can deal with this setting. I hope you've already seen the Steiner tree problem in some other courses, but even if not, the definition is very easy. Let's have a look at it. So in the Steiner tree problem, in its offline version, what do we have? We are given a graph G with vertices V and edges E, and we're given edge weights, which we call WE, which are non-negative, for all edges. And furthermore, we'll have a root vertex probably in the usual definition you won't see this root vertex, but this makes it easier for us to state the problems with uncertainty. And we'll have terminals, which is a subset of the vertices. Now our task is as follows. We'll have to find a subset S of edges such that R union T is connected in the graph that we get by taking the same set of vertices but only the edges in S. And our goal is to minimize the sum of the edge weights of the edges that we pick. Good. So what's this problem? We have a graph with edge weights, and then we have a set of terminals. Usually you'll only see the set of terminals. I now say we have an additional root vertex R, which is considered the same as a terminal. So in the standard offline definition, you'll just see this as one. This would be just one terminal. And what's now our task? Our task is to find a subset of the edges, which make sure that all terminals are connected to each other, which means that R and all terminals give us in a connected subgraph if we only consider the edges that are in S. But importantly, So what's this problem? Well, we are given a weighted graph with terminals, which is just a subset of the vertex set. And we are also given a root vertex, which usually you won't see in the standard definition of the online problem because you can just consider this one further terminal. And what are you supposed to do now? You're now supposed to find a subset of the edges with a property that R union T, so all terminals and the root, are connected in this graph, namely if you only use the edges in S. So the edges in S have to somehow connect all terminals to each other and to the root. The goal is to minimize the sum of the edge weights. This looks a bit like the spanning tree problem, and indeed it is a generalization of the spanning tree problem, because what would you have to do in the spanning tree problem? There, all vertices would be terminals, and so you just have to choose a subset of the edges so that all vertices are connected. This problem is called Steiner tree, like the spanning tree problem is called spanning tree, although we don't actually have the constraint that S has to be a tree. We are now stating it that this can be any subset of the edges, although, as you can easily see, you would always choose a subset, or the optimal solution always chooses a subset which is a tree, because having more than two edges on a cycle won't help you at all, and this will only be more expensive. Good. This problem is NP hard, so even in polynomial time you cannot hope to find a good or find the optimal solution, although it is not difficult to find a good solution. But this is not what we are trying today. We are considering a setting where these terminals are revealed to us one after the other. So this is the online version of the problem. And we'll have T as the set of T1 through Tk, and Ti is revealed in the ith step. And at any point in time, the set of R and T1 to Ti has to be connected in the graph with vertices V and edges S. And we may only add edges to S and not remove them. And I realized that actually I forgot to mention one assumption, namely that if we choose all edges, that then actually the terminals are connected. But of course we will only want to choose a subset of the edges. This is like in the spanning tree problem. This doesn't make sense if the graph isn't connected at all. Good. So what's now the online version? The online version is as follows. In the ith step, we get to see the ith terminal, and we'll have to make sure that this terminal has to be connected to the other terminals and to the root that have been revealed so far. Of course, we know that R and T1 through Ti-1, they are already connected. So effectively what we'll have to do in step I is to make sure that terminal I gets connected to the terminals that we already have. Let's see what this can look like. Let the graph just look as follows. We'll just have 4 vertices, and it looks like this. Now this should be my root, and this might be my first terminal. So this is revealed in the first step. And now I somehow have to connect this terminal to the root. And I should mention that all edge weights are 1 here. And now I'll have to connect this terminal to the root. How can I do this? Well, I will certainly have to choose 2 edges, at least 2 edges. Of course, I could, for example, take all the edges, then I would incur a cost of 4, or I can only choose 2 edges, but I have to choose 2 edges. So I could, for example, go via the top path or via the bottom path. Now at this point in time, both look equally good, so let's say we choose the top path. And now the next terminal is revealed to us, and if this upper vertex happens to be the next terminal, then we're in perfect shape because this is already connected to everywhere. Whereas if this happens to be the next terminal, then we are unlucky because then we'll have to add another edge. And so generally what you will see is that, okay, this could be T2 or this could be T2. And what will be the cost of any deterministic algorithm? In the worst case, it will be 3, but the cost of the optimal offline solution will be always 2, regardless of whether this or this will be the second terminal. So this already means that no algorithm will be better than 3/2 competitive or strictly 3/2 competitive, because we just have this very simple example where you cannot be better than 3/2. And indeed, even 3/2 you cannot achieve. The competitive ratios that we will be getting here will indeed even grow in the number of edges that we have in our graph. And this also has to be this way because this is the lower bound that we'll show afterwards. But before we get to the algorithm and then also the lower bound afterwards, let's first talk about how we can better understand the spanning tree problem, also the spanning tree problem, because how we can understand the Steiner tree problem and how this then relates to the spanning tree problem, because you might realize that those are actually similar problems, and indeed we can use an algorithm that solves the spanning tree problem also to solve the Steiner tree problem. In order to make the connection between the Steiner tree problem and the spanning trees, we'll first have to make some simplifications to our setting. Namely, what we can assume without loss of generality is that the edge weights follow the triangle inequality and also that we have a complete graph. Why is this? Well, in a Steiner tree, any edge which directly connects U to V can be replaced by a path starting from U, going via immediate vertices, and then ending at V. And this means that we should never choose E if there is a cheaper path from U to V. Why that? Because we might as well take the path, and this won't hurt our feasibility, but this might decrease our cost. And because of this observation, we can assume without loss of generality that G is a complete graph and the weights WE fulfill the triangle inequality namely that the weight of the edge from U to V is at most the weight of the edge from U to X plus the weight of the edge from X to V. And this holds for all U, V, and X. And why is this without loss of generality? Because otherwise we can just simulate the respective edge via a path. Good. So this is not super formal, but we are not really in a class on combinatorial optimization here, where you might want to make this more formal. We are actually introduced in the setting of uncertainty here. This is why I'm a little sloppy with all this, but I hope the point is clear. Namely that if we did not have the triangle inequality fulfilled, then there is never a point in using this direct edge, because we could just take the respective intermediate vertex and this way reduce the cost. Or, in other words, whenever we say add edge UV now to our set, what we actually mean is add the shortest path from U to V to our set. And this then fulfills the triangle inequality, because paths fulfill the triangle inequality. Good. And now we are able to state in this graph, where we have the triangle inequality, the connection between Steiner trees and spanning trees. The point of a Steiner tree is that it may even connect vertices which are not terminals to each other, to the terminals, and so on. So in principle, there may be these vertices which are called Steiner vertices, which just help us connect things. If we were considering instead the spanning tree problem just on the terminal sets, then this would not be allowed, just because these potential Steiner vertices wouldn't even be visible. And this is why these two problems are different, but we can use the optimal solution to the spanning tree problem on only the terminal set as an approximation to the optimal Steiner tree. What will this look like formally? So we say that MST of T, this is a subset of the edges, this is what we will call the minimum spanning tree on the graph induced by the root and the terminals. So this means here that only R and union T are vertices in this graph. And then we'll have also the set Steiner of T, which is the optimal Steiner tree connecting the root and the terminals. So what can happen here? Well, why are these two things different? Let's consider the following kind of a graph. We'll have here our K terminals, and the root, and they are connected to some other vertex which is not a terminal. So these are the terminals and the root. And, well, we now have this graph. The edge weight should be 1. Now, first of all, this does not yet fulfill the triangle inequality, or it's not even a complete graph because there is no edge between this and this vertex. But because of our assumption without loss of generality, we could always take this path via this vertex, which is not one of the terminals, which is just happens to be one further vertex. So then we would have this edge and this edge and this edge and these two edges and also this edge. They would all have a weight of 2. This is coming from the assumption that our graph is fully connected, and now these edge weights fulfill the triangle inequality. Good. Now what is this here? How would we find the minimum spanning tree on these vertices? Well, this vertex doesn't even exist. So we just have to connect these. And what will be the cost of the MST solution here? Well, we'll have to use 3 of these edges, and it doesn't actually matter which of the edges we're using. So generally speaking here, the weight of the MST of the terminals will be 2 times k minus 1. Because we would use the k minus 1 of the red edges. But what would be the optimal solution of the Steiner tree problem? Well, we would use exactly the black edges. We have k black edges, and so what would be our cost here? Our cost here would be equal to k. And to be precise, I'm now writing this as k minus 1 terminals and the root, so k would be 3 in this example here. One of these could be the root. I don't actually care. As I was saying, the standard perspective on Steiner tree is usually that there is no root, but it will turn out later that actually having the rooted version makes things easier for us. Good. So, certainly these two things are different. And what else do we know? The Steiner tree will always be cheaper, or will never be more expensive than the MST. Why is this? Because this choice here, this is certainly also a feasible Steiner tree. But indeed, as we were seeing, the Steiner tree may be cheaper, but it cannot be arbitrarily cheaper. The difference, or the factor, may only be a factor of 2. So the one observation that we have, of course, is that the weight of the Steiner tree will always be at most the weight of the MST in the respective induced graph, but there's also the other way around, namely that the MST will have a cost of at most twice the cost of the optimal Steiner tree. And this means we already have an algorithm to find, or an approximation algorithm to find an offline Steiner tree, namely just only consider the graph, the subgraph that is induced by your terminal set and the root. And on this, just solve the Steiner tree problem, the spanning tree problem, which you can do in polynomial time. And by just combining these two things, you will see, okay, your solution will be a true approximation of the optimal Steiner tree. What's the idea to prove such a lemma? Well, what we can do is we can double all edges in the Steiner tree. And then we can traverse through these edges in an Euler tour. So let's maybe try to see this a little more graphically. This might be our Steiner tree. Now what we'll do is we'll double all edges. And this is what it will look like. So this is after having doubled all edges. And then we will find the Euler tour. So this means nothing but that we find a tour through all the edges in this graph. And this is now possible because the graph of the degree of every node is even after we've doubled the edges. So let's just see what this might look like. We might go to the graph like this. Going through exactly each edge once. And now I didn't even mention which of these nodes are the terminals. Well, some of these are the terminals, of course. But the important thing is we will, on this tour here, we will see every vertex in this tree at least once. So in particular, we will see each terminal at least once on the tour. So this might be my terminals, say, and we can also see them here. They are visited at least once, so this terminal here is even visited multiple times. And now what we do is we will shortcut the tour to only visit the terminals. So what will this look like? This is our graph and our Steiner tree, and now we just shortcut the tour so that we see that we only see the terminals, which means that rather than going from here to there and from here to there, because this node is not a terminal, and maybe I might want to say that this up here is the root. And then what I should do is I should go directly from here to here, and then I'll only go through the graph as I was seeing the things, the vertices on the tour, like I was doing here. So here I was going this way, 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 and so on. And now what I'll do is I'll just shortcut everything to only the point where I see a terminal for the first time. And what we now have is that the shortcutted tour is a path in the graph, in the subgraph induced by the root and the terminals. And it is at least as expensive as the MST will have in this graph, because it covers all because it visits all vertices in this graph, and it is a tree. And it is at most as expensive as the Euler tour. And what was the cost of the Euler tour? Where did the Euler tour come from? The Euler tour was a traversal through the Steiner tree, where we were going via each edge in the Steiner tree twice. Good. So this means that its cost will be at most 2 times cost of the optimal Steiner tree. So overall we'll get that the cost of the MST will be at most 2 times the cost of the optimal Steiner tree. And where did this come from? I might have said before, I should have said before, this is because of the triangle inequality. Here it is important that shortcutting these things, so rather than going via this hop in between, directly going via this edge, things will only become cheaper. Good. So this gives us already one way of finding a Steiner tree or finding something that is close to the optimal Steiner tree. Close is maybe a relative term here. It is only within a factor of 2 of the optimal Steiner tree, but given that we're trying to solve the online Steiner tree problem here, this factor of 2 actually will become negligible because we will see much bigger factors coming in because of the uncertainty which terminals we will have to connect. And this is what we'll do next. We will next introduce an algorithm for the online Steiner tree problem. Now we are finally able to design an algorithm for the online Steiner tree problem, and this algorithm will actually be extremely simple. It is a greedy algorithm, and what we'll do is we will simply connect a terminal when it arrives the cheapest possible way. And as we've made the assumption that the triangle inequality is fulfilled, we can just take one edge to the existing terminals that have already been added before. So we'll take the cheapest of these edges, and this makes sure that also the new terminal gets connected. So formally we would write this as follows. We will initialize S as the empty set, and when Ti arrives, we let Ei be the cheapest edge between Ti and any of Rt1 and so on up to Ti minus 1, and then we'll add Ei to S. And what we claim is that this greedy algorithm is strictly O of log k competitive. So our sequence has length k because we're adding k terminals, and our guarantee is now that our competitive ratio will be O of log k. Good. How will we prove this? Well, what we'll have to do is we'll have to bound the cost of the edges that we're adding to our solution. And how do we do this? Well, ideally, or in the easiest way that is imaginable, we would just say, okay, the cost of Ei is at most this much times opt. Well, this is not really true, but we can say something similar, namely what is the jth highest cost of all the edges that we are adding. We're adding in total k edges, and now what is the most expensive of these edges? What's that cost? Or the second most expensive, or the third most expensive? And we will now derive an upper bound for any possible j. What is the jth expansive edge that we're adding throughout the execution of the algorithm? And namely, what we are deriving is the following bound. The jth highest of the weights of the edges E1 through EK is at most 2 times the weight of the optimal Steiner tree on all terminals divided by j. So the cost of the most expensive edge that we're adding will be at most for this j is 1, so this will be at most 2 times opt. For the 25th most expensive edge among the ones that we're adding, we'll have at most 2 times opt over 25. And if you're familiar with the harmonic number, you'll see, okay, these things will up to something in the order of log k, but this is what we're coming to only afterwards. Let's first prove this lemma. We let Tj be a subset of the terminals, and these are the j terminals for which the connection cost is highest, which means the respective W of EI is highest. And now we claim that the minimum of all I and Tj weight of edge I is at most 2 times the weight of the optimal Steiner tree divided by j. So I hope you see that this is actually nothing but a more formalized way of our lemma. We now consider the Tj as the set of terminals for which the connection cost is highest, which means the respective edge that we're adding. And among these, we ask what is the cheapest of the edges. So this is nothing but the jth most expensive edge that we're seeing. Good. How can we bound this? Well, what we'll do is we'll consider the MST of Tj. And what do we see? We observe that MST of Tj contains exactly j edges, because those are connecting these terminals to each other and to the root. And what does this mean? This means that the smallest of the edge weights in this MST this is at most the average edge weight in this MST. And this is nothing but the weight of the MST divided by J. And now let E be the cheapest edge in this MST of Tj. And we'll write E as Ta to Tb because it is connecting two terminals where A is smaller than B, and let's just say that T0 we'll call the root. So we'll have this MST on this set Tj, and we're now asking, well, what is the cheapest of the edges that we have here? And for the cheapest of the edges, we'll ask, what is the terminal that arrives earlier? Maybe it is the root. This is just what we'll call T0. Or maybe just some other terminal, but there is one terminal that arrives before the other. So this is just an edge connecting two terminals. And what we're now claiming is that TB could have used edge E in our greedy algorithm to be connected to the other terminals. Because at the point where TB arrived, TA had already arrived. And this means that the cost that TB incurs for connecting itself to the other terminals will be at most this much. So this then means that the minimum of the W of EI will be at most this much. So when TB arrives, TA has already arrived. Therefore, E is a feasible choice for EB, which means that the minimum of all I in Tj, W of EI, this will of course be at most the cost that terminal B had, which was one endpoint of these edges E. But this edge could also use, this terminal B might use this edge. Now, how expensive is this edge? This is the cheapest of all, so this will be at most the cost of the MST of Tj divided by j. Now this is at most the 2 times the cost of the optimal Steiner tree on Tj. And Steiner trees only become more expensive if we have more terminals. Because in this step, this thing here would also be a feasible solution for this one. And so this proves our lemma, which was claiming that the jth highest of these edge costs is at most 2 times the cost of the optimal Steiner tree on all terminals divided by j. Good. Now with this lemma, things become super easy, fortunately, because what we'll have to do now is just we'll have to see the following, namely, what is the sum of these weights of the edges EI? Well, we might alternatively say for the most expensive, for the second most expensive, and so on, we'll add up these respective terms. And what we are left with here is 2 times the cost of the optimal Steiner tree. And this we multiply with the sum from j from 1 up to k of 1 over j. And this thing here, this you might recognize as the kth harmonic number. And what do we know about the kth harmonic number? We know that we can upper bound it as follows. We can upper bound it by, well, what's this thing? How can we interpret this pictorially? The function 1 over x. And now see what's happening here. We are actually trying to sum up the area of all these rectangles. But instead we could take 1 plus the integral from 1 to k of 1 over x dx, and this would be 1 plus ln k. So this proves that the sum of all edge weights of the edges that we're adding is at most 2 times the cost of the optimal Steiner tree plus O of log k. Did I say this correctly? This And this proves that the cost of the edges that we choose is at most 2 times the cost of the optimal Steiner tree times O of log k. Great! So we've seen an algorithm that gives us a competitive ratio of O of log number of terminals. This, of course, feels much worse than what we were talking about last time, like constant competitive ratios. Could we also hope for a constant competitive algorithm here? Well, unfortunately, the answer is no. And as we will show now, no deterministic algorithm can actually be better. This general statement also holds for randomized algorithms, but the technique to show this for randomized algorithms we haven't seen yet. This is something we'll see later in this class. But what's the statement? The statement is as follows. There is no strictly alpha competitive deterministic algorithm for alpha being in small o of log k, where k was the number of terminals that we have. Let's try to prove this. We consider an arbitrary deterministic algorithm and without loss of generality, we assume that whenever it picks an edge, it only chooses a simple path without any terminals except for the endpoint. Okay, this sounds super annoying because this is just what we allowed our algorithm to do so far, was to choose as many edges as it liked. Now let's just restrict our attention to algorithms which do not choose more edges than they have to. So they only connect the current terminal to the previous terminals of the root. And by doing this, they just choose one path. They don't choose like 2 paths, or they go beyond the terminals. Whatever they might be allowed to do, this will only make the algorithm worse. But for us, this simplifies the life, because we can now eventually we'll see that, okay, there has to be an area in the graph where the algorithm has not yet picked any edges. Good. Now we will construct a graph and a sequence of terminals on this graph. We consider the case that k, so the number of terminals that we should have, is a power of 2, and we set L to be the log to the base 2 of k. And now we define the diamond graph, which I want to call dj of level j as follows. What's d1? d1 is nothing but the graph that we've already seen before in our example, where this was our root, this was our terminal, our first terminal, and then this or this was the next terminal. And now we'll have that dj plus 1 is defined as follows. We'll have 4 vertices, and now here in between we'll have a graph dj, and here we'll have a graph dj, and here we'll have a graph dj, and here we'll have a graph dj, which each have again a left endpoint and a right endpoint, and in between we put such a diamond graph of the level below. So what will this look like? So D2 would be, we again have this structure, but now what we'll have is this D1 graph will have actually 4 times replacing the edges in the respective D1 graph. So this is what the D2 graph looks like. Now what will the D3 graph look like? Well, we could take this perspective and now say, okay, each of these will be graphs like this, or equivalently you could also say replace any of the edges again by such a D1 graph. And what will you see is that there in dj there are exactly 2 to the j edges from the left to the right node. So what do I mean by left and right? I mean that we now have here, this is what we will call the left, and this is what we will call the right node. And respectively, this is the right node of this graph, and it is the left node of this graph. And eventually we will now define in this graph a sequence of terminals such that our algorithm will have a poor performance compared to the offline optimum. Namely, what will this look like? This actually will look exactly like what we saw earlier in the D1 case. This is our root. This is our first terminal. And then the algorithm will either choose this path or choose this path. And then, depending on what it chose, because it is a deterministic algorithm, we can actually anticipate this. We choose the sequence which has this or this terminal as the second one, so always the worst of the two choices. We can do the exact same thing here, namely this is our root, this is our first terminal, then we will have either this kind of a path or this kind of a path. This is where we use our simplification regarding the algorithm, that the algorithm only chooses a path, because this means now either this upper half hasn't been touched upon or this lower half hasn't been touched upon. There has no edge been chosen so far. And then we will choose this or this vertex, and then we'll recurse to the respective graphs on the lower level. Good. Let's write this down a little more formally. So we will define a sequence of terminals in DL. The root is the left node in DL. The first terminal is the right node in DL. And this is what we will now call phase 0, because we'll now define phases 1 through L, in which always 2 to the I-1 terminals are requested. So this will be our I. And what does this look like? How do we define these phases? We will now maintain an invariant. Namely that, as I was saying, at the beginning of the first phase, we have this as our first terminal. And now what will happen is that the algorithm chooses either this kind of a path via the top half or via the bottom half. And what's now our invariant? Our invariant is that there are for the first phase we have 2 of these graphs on one level lower, which do not contain any edges and which are just on connected like this, so that we have the left node, then we have a one other node, and then we have the right node. And this is exactly our invariant that we'll also maintain later on. Namely, what we'll have as will be as follows. at the beginning of phase I, there are 2 to the I minus 1 induced subgraphs and now let's be careful what we mean by this. We mean that those are subgraphs which are like this, which are each isomorphic to the diamond graph of level L minus I plus 1. And there are no terminals there except for the left and the right node. So at the beginning of phase 1, what we'll have is, what was our number saying? We'll have 1 induced subgraph without any terminals except for the left and the right node. So this is what it will look like. We have just this one graph. And what we'll now do is this or this will be our respective terminal that we're requesting now, depending on how the algorithm chose to connect the left and the right node. If it chose to connect them this way, then we choose this terminal. If it chooses to connect them this way, then we choose this terminal. And afterwards, what do we have? We will then again say that we are choosing now this terminal, then we'll have again some subgraph here and some subgraph here, which again have the same property that only the left and the right node are terminals, but nothing in between. So this then, on a smaller scale, looks exactly like this bigger picture. Good. So we construct phase I as follows. In each of the graphs dl minus I plus 1, the algorithm has chosen exactly one path from left to right. So far. And we request as a terminal the central node at the bottom or the top, which is not contained on this path. What does this mean? This now means that we'll have requested, say this one, because our path was going this way, and now we'll have the invariant still maintained that we requested a terminal here, and here we have another two graphs, which then maintains our invariant that now we have double the number of induced subgraphs, which are isomorphic to the diamond graph of one level less. So the invariant is maintained by the diamond graphs left and right of this terminal. What will be our cost? Well, what's the cost of the optimal solution? It will be 2 to the L, because all terminals are on a single path from left to right. And what's the cost of our algorithm? Well, one step in phase I costs 2 to the L minus I, because what we're doing is we are connecting in this graph here. We'll have to choose either one path this way or this. They both have the same length, so this will be our cost for this one choice, and there are how many steps in phase I? There are 2 to the I minus 1 terminals in phase I. So what we'll get is the total cost of, take the sum over all, well, we'll have a cost of 2 to the L for phase 0, and then we'll have for every later phase, what cost will we have? We'll have a cost of 2 to the I minus 1 times L to the 2 to the power of L minus I, And this is exactly 2 to the L plus L times 2 to the L minus 1. Which means that the cost that the algorithm incurs divided by the cost of the optimum, this will be exactly 2 to the L plus L times 2 to the L minus 1 divided by 2 to the L, and this is 1 plus L over 2. And why do we have exactly k terminals? Or how many terminals do we have? We have eventually on every node or every edge on this path corresponds to exactly one terminal. So this will also be exactly 1 plus log the base of 2 of k divided by 2. Good. So this is a bit ugly to write down, but I think the idea is pretty easy. Namely, what you'll do is actually you take this diamond construction that we had at the very beginning, and then recursively you again hide this diamond construction again and again in there. And if you then do the math, maybe it's a little hard to follow this online, but what you will eventually see is that in every of these steps, in every of these phases, what will happen again and again is what was happening in the original example, namely that you'll have to pay for this additional terminal. You have to pay half of the length of the path that you already had before, with the addition that you could have already chosen to cover this terminal before if you had only known that this was the terminal to come up. You can also extend this to randomized algorithms. Actually, the same construction will hold. You can just do it the same way. Then you would have to argue a little more carefully, because here we were not saying, okay, we can just anticipate what the algorithm is doing. There, what you'll actually do is you'll just, as the instance, you'll flip a coin, and then you'll use something that is called Yau's principle, which we'll see later this semester. For the time being, what is important here is that you'll see, okay, we have this very simple algorithm, easy to analyze, and then we also have the lower bound where you can see why this lower bound is actually true and why we couldn't have done much better than what we did in the case than what we did with the greedy algorithm, at least in terms of the competitive ratio. Of course, the question might be, in other models of uncertainty, maybe there you could do much better if you had additional information. And this is indeed something that we'll be considering later in the semester. What if you have additional information here? Good. But before we get there, we'll first stick to online algorithms for a bit, where we have no prior knowledge of what's going to happen. We'll keep doing this online competitive analysis. And for this, next time we'll introduce a much more general framework than what we had so far. So far we just had some algorithms here and there. Next time we'll see a much bigger picture of, well, how can we in general design algorithms, design online algorithms in a much more structured, fundamental way. This is it for today. Please let me know if you have any questions. I hope that you stay with us until next time. In the meantime, stay safe. Bye.